Welcome back to this introductory lecture on proof techniques. In this sixth segment, we're going to introduce yet a different kind of proof technique called a direct proof. Like the two previous proof techniques, vacuous proofs and trivial proofs, this one applies to theorems that are stated as conditionals. So what happens when you can't prove that P is always false, or you can't prove that Q is always true? In other words, you can't apply the two previous proof techniques. How do you prove the conditional P implies Q? Well, one way to do that is to use a proof technique called a direct proof. And the way this works is to assume that P is true. That's the starting point of the proof. And using that assumption alone to infer that Q must also be true. Now remember, by definition, the material implication P implies Q is true. That means whenever P is true, Q must also be true. So that's why the direct proof technique works, because it says I'm going to assume that P is true, and I'm going to try to infer that under this assumption Q must also be true. Now to illustrate this proof technique, let's look at yet another propositional function P of n over the same universe of integers z. And this time P of n states that if n is odd, then n plus 1 is even. So notice P of n is not a proposition, so as the fourth theorem in this lecture, we're going to prove the actual proposition P of n bar, where n bar is a specific but unknown or arbitrary integer. So let's start our proof. Since we're using a direct proof and the theorem is a conditional, we're going to assume that its hypothesis is true. And the hypothesis is that n bar is odd. So that's our assumption for the duration of this proof. From that assumption alone, we must be able to infer that n bar plus 1 is even. So let's do it. From the assumption that n bar is odd, and by definition of being odd, we can infer that there exists an integer k such that n bar is equal to 2k plus 1. Now we can add 1 to n bar to obtain the equality n bar plus 1 is equal to 2k plus 1 plus 1. That's simple and trivial arithmetic. Then we can rewrite the right-hand side of the equality by grouping 1 plus 1 into the integer 2. Again, that's trivial arithmetic. No need to justify it in writing. The next step is to infer that the right-hand side is equal to 2 times k plus 1, which is obtained by factoring out the 2 in the two terms 2k and 2. So what this means is n bar plus 1 is equal to 2 times k prime, where k prime is the integer k plus 1. So all we are doing here is giving a name to that number k plus 1, and we just say it's called k prime. What's important though is to argue that k prime is actually an integer. As you'll see, we need that in the second step, or the next step. So why is k prime an integer here? Well, it must be an integer because from this step, we know that k is an integer, and we know that every time you add 1 to an integer, you obtain another integer. So again, we just proved that n plus 1 is equal to 2 times some integer k prime. So now we can use existential generalization to infer that there must exist a case such that n bar plus 1 is equal to 2k, and the particular value of k in this case is k prime. But that is just the definition of being even. In other words, we just proved that n bar plus 1 is even. And that's the conclusion of the conditional that we're trying to prove. So, to recap the proof, we assume that the hypothesis of the conditional was true. We inferred from that that the conclusion of the conditional was also true, and therefore we proved the theorem. And that concludes our 6th segment.